In this video, we will make an effort to conceive of some of the technology that would be of assistance to the first colonists of Mars, should such a scenario come to pass. We will make every effort to understand the challenges they could face as well as the potential solutions. It will take a very long time, at least 6 or 7 months, for the crew to reach Mars alive. During this time, they will be completely exposed to an adequate quantity of cosmic rays and ionizing radiation, the impacts of which in the long run could be detrimental to the health of an organism, leading to a high likelihood of developing serious illnesses. This is the first significant challenge. How can we find a solution to the issue that does not involve using very heavy lead or large radiation shields? Welcome to the Technology Zone, where the home of technology resides. Here are some great technologies that you should not miss, as these innovations can help in the future colonization of Mars. At the Ames Research Center in California, they have devised and are testing a compactor that appears to take the regular non-organic waste production in flight and convert it into a disk approximately 20 centimeters in diameter and 1.5 centimeters in thickness. This disk can be used to assemble a light and handy cosmic ray shield that can be attached to the wall surfaces of the space vehicle, a form of tile in size that has the ability to absorb the harmful radiations of particles that flow through the distances between planets owing to the presence of plastic that has been compressed at least 10 times inside its composition. Carpeting one of the areas within the spacecraft, such as sleeping area or even establishing a refuge area to be used for short periods of time in the occurrence of a violent explosion by the sun, would allow astronauts to be secured without needing to carry the load of a traditional shield composed of thick metal. This would be advantageous in the event that astronauts are required to remain in the spacecraft for an extended period of time. A reasonable objection could be made that the waste can be thrown out of the capsule, which would be an effective solution despite the fact that it would not be elegant and would go against NASA's ethics. Filled with lots of bacteria as well as other potential pathogens agents, like anything that comes into contact with humans, the waste could lead to contamination of other planets. What course of action would you recommend taking? Please put it in the comments down below. Although the compactor is relatively tiny, it heats the material to 150 degrees for 3.5 hours, which is hot enough to kill any microorganisms but not hot enough to risk burning the material. Half a kilogram of everyday items for living in space, such as water bottles, plastic tape, food wrappers, aluminum cans, and foil wrapping, are required to produce a 20 centimeter circular shield tile. It's still unclear how long the compressed material can survive, and more importantly, considering that it's utilized to furnish spaces where people spend countless months, whether a healthy or at least neutral atmosphere is generated. Another significant issue with space missions that this technology would simultaneously address is the storage of crew waste. The Water Walls project is an alternate project that NASA has presented. This project intends to utilize either potable water or wastewater in order to shield astronauts from cosmic rays. Water molecules, which are made up of 3 tiny atoms, contain more nuclei per volume than metal does. This is because nuclei are liable for blocking cosmic rays, and water molecules, which are made up of hydrogen bonding, contain more nuclei per volume. Marco Durante of the Technical University of Darmstadt says that this is why water is a better protection than metal. In addition, the water that was utilized as a barrier is safe to drink, even if it was obtained by collecting people's urine and feces. In point of fact, the water wall system makes use of polyethylene bags, which, when submerged in water, undergo an osmosis process that cleans the water and provides astronauts with a steady supply of drinkable water. These bags will be initially filled with drinkable water, but over time, that water will be replaced with water that has been recycled from the crew's biowaste. The final thickness of this protective layer will be 40 centimeters. The Water Walls project also includes the use of bags that are capable of removing excess carbon dioxide from the air, changing the temperature of the shuttle, or producing microhabitats that are conducive to the development of algae and plants. Despite this, plenty of issues still need to be resolved. Although the radiation shielding bags have previously been tested in space during the most recent flight of the space shuttle, the effectiveness of these bags in a microgravity environment is only half of what has been demonstrated on Earth. This is insufficient to keep a crew alive while being subjected to constant doses of radiation. Ruth Bamford, a researcher at the Rutherford Appleton Laboratory, who was responsible for the creation of a magnetic solar radiation shield, explains that in the event of solar flares, it is doubtful that even concrete protection that is 10 feet thick would indeed be able to protect astronauts from the harmful radiation. And to get around this problem, the shuttle's last stage of the launching rocket might remain linked to the shuttle at all times. This would allow the shuttle to face the sun whenever significant amounts of radiation were being released into the atmosphere. As soon as they have successfully landed on Mars, astronauts will then be confronted with a second significant challenge. This challenge will involve the generation of energy and biofuels for the missile systems that will be employed to travel back to Earth using the assets already there, such as carbon dioxide, sunlight, and ice water. Cyanobacteria, which will absorb carbon dioxide from the Martian atmosphere and also use sunlight to generate carbohydrates, and E. coli, which is designed to convert those carbohydrates into particular rocket fuel for launchers, as well as other propulsion equipment. Both of these terrestrial microbes need to be brought to Mars in order to initiate the bioproduction procedures, as described in an article published in Nature Communications. This mixture already occurs on Earth and is known as 2,3-butanediol. It has the equation CH3CHOH2, and the rubber industry uses it to manufacture polymers. Methane and liquid oxygen, or LOX, are the fuels for today's rocket engines, which may soon be able to land on Mars. However, none of these substances is found in large quantities on the red planet. They would need to acquire them from Earth first. Furthermore, the transportation is rather pricey. It is anticipated that the trip of 30 tons of methane and LOX would cost around $8 billion. NASA and other organizations have proposed several solutions to derive the two components on the spot. Yet, these technologies are still in their infancy and cannot yet function on a big scale. The idea put up by the Georgia Institute of Technology asked for the exploitation of in situ resources via the application of biotechnology, intending to generate propellant and LOX from CO2. In addition, the procedure would return 44 tons of clean oxygen surplus, which might be stored for use in other applications, such as facilitating human colonization. And to begin, the necessary plastic products would need to be sent to Mars in order to construct photobioreactors that are the size of 4 American football fields. Through the process of photosynthesis, cyanobacteria would proliferate in reactors, which require carbon dioxide. In a separate reactor, the enzymes would convert the cyanobacteria into glucose that E. coli could use. This glucose would then be used to produce the rocket fuel. What are your plans in the event that this procedure fails for some cause and it is therefore impossible for you to return to Earth? Please put it in the comments down below. According to Pamela Peralta Yaya, one of the authors of the research and a professor at the School of Chemistry and Biochemistry and CHBE, who creates microorganisms for the manufacture of chemicals, this technique requires considerably less energy to lift off from Mars, which has provided the freedom to explore alternative compounds that are not meant to fire rockets to Earth. Additionally, she claims that this process could be utilized for the creation of a wide range of different chemicals. In order to come up with methods that are not applicable to launches from Earth, people have started looking at different ways to take advantage of the planet's reduced gravity and oxygen shortage. The group is making preparations to carry out the biological and material improvement that has been discovered to produce a linear and quick process. For instance, enhancing the pace at which cyanobacteria grow on Mars would call for a photobioreactor that is an ever-increasing amount smaller, which would significantly reduce the payload that would be necessary to bring equipment from Earth. However, further research is required to demonstrate that cyanobacteria can thrive in Martian environments, And it is also essential to take into account the unique solar spectrum that exists on Mars as a result of the planet's greater distance to the Sun and its absence of an atmosphere that can absorb some of the light that reaches the surface. Cyanobacteria might be harmed by exposure to high quantities of UV light. The generation of oxygen is yet another crucial problem for the continued existence of a ship's crew. The Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, was an experiment that was put aboard the Perseverance rover. It demonstrated that it is feasible to produce oxygen from the Martian atmosphere. Oxygen will be an essential component for future exploration of Mars, and not only because it is required to maintain astronauts' lives. The rockets can also function when propelled by liquid oxygen, but in order to flee from the red planet, it is required to be able to manufacture the propellant on site. The MOXIE rover successfully became the first to harvest 5 grams of oxygen from the Martian atmosphere. This marks yet another important milestone in space exploration. Nonetheless, it begs the question, how is it even feasible to extract oxygen from a surrounding air that does not contain any? In reality, just 0.16% of the atmosphere of Mars is made up of oxygen, O2 to be exact, but this isn't what MOXIE is collected from the surface of the planet. Carbon dioxide, or CO2, which makes up 96% of the atmosphere, was gathered by the NASA experiment on April 20th at Sol number 6C. This was the first time the instrument had been turned on since it was activated on April 20th. After obtaining CO2, MOXIE proceeded to break it down, which resulted in the collection of oxygen and the discharge of carbon monoxide into the planet's atmosphere. Since the Ingenuity helicopter is not a genuine scientific experiment, the experiment is only a technical demonstration intended to demonstrate new technology. The investigation is carried out inside the confines of the Perseverance rover, which is comparable in size to a toaster and weighs 17 kilograms. As stated before, the transformation of carbon dioxide into carbon monoxide and oxygen is supposed to be the end result. The first portion is kept in storage, while the second is released into the atmosphere. Following the first activation of MOXIE, a total of 5.37 grams of oxygen was generated. This quantity is about similar to breathing air for 10 minutes. However, MOXIE was meant to provide up to 10 grams per hour of oxygen. In order to complete this transformation, it makes use of a process called solid oxide electrolysis, which involves compressing and heating the atmosphere of Mars. Additionally, it must maintain temperatures up to 800 degrees Celsius for the duration of this procedure. Because of this, the whole of MOXIE has been painstakingly constructed to withstand extreme temperatures and to separate them to the greatest extent possible so that they do not cause harm to Perseverance. Some of the parts are constructed out of nickel alloy, and they are responsible for the cooling and heating of the gases collected. Furthermore, there is a golden coating on the outside of the device, reflecting infrared radiation and preventing it from radiating outside the device. In order to evaluate MOXIE in the widest variety of environments feasible, the program will now run in 3 distinct stages. The current production that has just been carried out is already an exceptional initial result, but first and foremost, the state and functioning of the device itself will be examined and evaluated. After then, the procedure will be performed in a variety of climatic circumstances, such as at a different time of day or during a different season. During the third and final phase, MOXIE will be pushed to its limits by being subjected to a variety of temperatures during testing. According to estimates provided by NASA, in order to return to Earth from Mars, 4 astronauts will need around 7,000 kilograms of fuel and 25,000 kilograms of oxygen. It is very improbable that 25 tons of oxygen could be transported straight from Earth to Mars. Instead, the astronauts would use up around 1 ton of oxygen during their 1-year stay on the planet if they stay there for the whole year. As a result of this, NASA is already planning the experiment that will take the place of MOXIE. It will be pretty similar to MOXIE, but it will be much more significant. A comparable device that weighed 1 ton could generate around 1 kilogram of oxygen in an hour. An apparatus of this kind could generate 25 tons of oxygen on Earth in 3 years. It would be sufficient to own a minimum of 5 of these gadgets in order to cut the duration down to 6 months. A 3D printer is another technology that must be included in human expeditions to Mars. Given that shipments of supplies would only come once every 26 months, the astronauts will need to be entirely self-sufficient and able to construct their own equipment and replacement parts. The Tissue Engineering and Additive Manufacturing Laboratory at Northwestern Engineering proved that it is possible to produce items using synthetic reproductions of lunar or Martian dust. This was done as part of the laboratory's demonstration of the feasibility of making such products. It is conceivable to manufacture specialized inks for 3D printers by combining regolith from Mars, a few different types of basic solvents, and a biopolymer. With these components, one might manufacture a set of bricks similar to Lego. The artificial dust particles that are utilized in the lab have a composition, shape, and size that are remarkably similar to that of the dust found on the Moon and Mars. After that, the 3D items such as tools and bricks were produced using a straightforward extrusion method. After that, identical bricks may be employed as structural components in the buildings. The researchers guarantee that the finished products may be bent and stretched while maintaining their strength when using this procedure. The material is highly comparable to rubber and may be handled, sliced, or wound. It also has these capabilities. To put it simply, it has the potential to be helpful on the planet Mars. The subsequent phase will involve making this material as brittle as pottery, and the only way to achieve so is to heat it in an oven similar to how it is performed on Earth. What are some more cutting-edge technologies that spring to mind while thinking of colonizing Mars? Please put it in the comments down below.